everyone. It's my pleasure to start with an introduction. So my talk will be mostly introductory. I will show basically what are we talking about. So what is quantum safe communication, the two paths, and I will also show briefly what we do at BeQCI. You see here the logo and all the partners of the consortium, but we'll talk about it more later. So as I said, I will give a brief introduction on why do we need quantum security and I will guide you through a brief history of the classical encryption, very outlined, and I will show what is the quantum threat and what are the possible solutions, which are both explored in our project. And then Giacomo, I will show you also. Yes,
Giacomo, sorry to interrupt. Would it be possible to move your microphone a little bit further? We're getting a bit of yeah.
Sorry, like this is better.
Yeah, thank you.
Okay. Yeah. So okay. Yeah, and then I will show you the possible solutions and also give an overview of the project, what we are doing and what we will do in the future. So let's start with classical encryption. So that's what we are talking about. And the basics of encryption, what was done in the past and what has been done for centuries now, is so the encryption answers the question on how we communicate securely. So if we have two parties, Alice and Bob, this is the most schematic situation, and they want to establish a communication channel. And they want this communication channel to be secured, so that only Alice and Bob exchange the information they exchange and no one else. And what was done in the past, Alice and Bob would meet up at a place and share a key, which is just a string of bits. They share this, they both have the same one, then they separate, they go on their own ways. Yeah, and okay, they go on their own separate ways and they establish a communication channel. They then use this. They want to use this communication channel along with the keys to communicate in a secure way, such that if there's an eavesdropper, so a third malicious party that taps into the communication channel, the Eve doesn't get any information on the message. So what was done is that Alice takes the message, for example, this nice message to Bob. She sums it with the key. She combines it with the key to create a ciphertext. And this ciphertext is sent through the communication channel to Bob, who can decrypt it with the key. And without the key, Eve is not able in any way to decrypt the message. So this is a secure way to communicate, but it's highly impractical, especially if we have a large network, so many parties communicating all together, because we want all of them to have the same key, and they have to meet up together to establish the key. So what was developed is an alternative scheme, which is called public key encryption scheme, which does not require the parties, in this case Alice and Bob, to meet up at a place and share key. And in this public key encryption scheme are the most common are as follows. We have Alice and Bob, they have their communication channel, and Alice generates two prime numbers, two very large prime numbers, multiplies them together to get what is called the modulus. And then she announces this modulus to the public. And this modulus is available to everyone, both Bob and eavesdroppers. Bob then prepares his message. He uses a particular algorithm which uses the modulus to encrypt the message and create a ciphertext. And the ciphertext is then sent back to Alice. And Alice can use both prime numbers, and she needs to use both prime numbers to decipher the ciphertext. And the essence of this communication scheme So why it works and why it's secure is based on the algorithms that ensures that if a party does not have the two prime numbers, so the two factors of the modulus, Eve, she cannot decipher the ciphertext. And okay, and so this whole scheme is based on the fact that factorizing numbers is hard in general, so that Eve cannot factorize the modulus. And this is exactly the case. So it's been known for a long time that on classical computer, prime factorization is a hard problem. What we mean with a hard problem, it means that it scales exponentially with the length of the number. So the longer the number, the longer it takes for a computer to factorize the number. And it scales exponentially. So we have we need exponential time compared to the key length. And this graph shows it very well. We have on the y-axis the complexity, so the time it takes for a classical computer to break this encryption scheme, so to factorize a number. And on the x-axis we have the length of the number. And we can see that since the scaling is exponential, as soon as we have a long enough number, a classical computer will take the age of the universe to crack. So it's the scheme is virtually secure because there's no classical computer that is able to crack the encryption by factorizing the number. Okay, so this is what we have now, and this now is secured. But let's focus a bit out and look at quantum computers. So what are quantum computers? Quantum computers are devices based on which use the specific oddities of quantum mechanics to perform some tasks in a much faster way. And it's a promise because we don't have quantum computers right now, or at least not big enough, let's say. But the promise is to have to bring advantages to many tasks, like for example, simulations of molecules to improve to discover new drugs in pharmaceutical applications or material science. Also promises to solve some logistic optimization problems way faster, and also spinning up some mathematical tasks, like, for example, prime factorization. In fact, it's been known for 40 years now, around that there is a quantum computer algorithm that is able to factorize to factorize number in an efficient way. And efficient means that the scaling is no longer exponential, that the complexity scaling or the time scaling is not longer exponential, but it's polynomial, which means that increasing the length of the key does not make the task impossible anymore or too long anymore, which means that a quantum computer will be able, when quantum computers will be available, quantum computers will be able to factorize prime numbers efficiently, and thus cracking the encryption schemes that we use currently. And just to give you an idea on the quantum computing development, one might say, but no one is developing quantum computers. I mean, we are hearing a lot of news about that, but that's also not true, because there's a lot of companies, and here is a non-exhaustive, in no particular order, list of companies involved in quantum computer, either directly or indirectly. And you can see there's a lot of effort put in developing quantum computers. So we don't know, we are not sure on when the quantum computers will be available. Depending on who you ask, you'll get different answers. But we are sure that a lot of effort is being put in it, and when we put a lot of effort into something, usually we are able to develop it. So soon enough, we will have quantum computers. So what we have to do is we have to be ready. we have to be ready, and we have to prepare for this quantum threat. And parallel to the quantum computing market, also there is a whole development of solutions to this problem, because of course when this problem came up at the beginning, people started looking into ways to encrypt the data in a way that it's secure even against quantum computers. And there are two main solutions. The first one is quantum cryptography, which is a new cryptographic scheme which also exploits quantum mechanics, but on the other side, to encrypt in a secure way, encrypt data in a secure way. And the advantage of quantum cryptography is that its security is based on the laws of physics. So we have ultimate security. There will never be any way to crack these schemes, because it's based on the fact that quantum mechanics is real. So if it's cracked, it means that quantum mechanics it's not true anymore. And this is good because when using quantum cryptography, one is sure that his data will be secure for forever. However, the disadvantage is that it requires dedicated hardware, which is expensive, and there's a lot of technical challenges. On the other hand, we have what is called post-quantum cryptography, which is based on it's basically using the same cryptographic schemes we use now, but with different algorithms. And this has the advantage that it's easy to deploy because it's just software updates. So it can be deployed on a mass scale, but the disadvantage is that these schemes are still based on assumptions, like the one based on prime factorization. And since it's based on assumption, it can be that there will be new algorithms or new ways of computing that break these algorithms. So it's safe until it's not. But on the other hand, it's very easy to deploy. And these two solutions are not in competition in any sense, but they're let's say suited, since they have strength and weaknesses. They're suited for different applications. Like quantum cryptography is clearly more suited for high-level applications, like public institutions or very sensitive data centers, hospitals, banks, where data is very sensitive and needs to be secured for a long time. Whereas post-quantum cryptography is more it's more suited for immediate applications. So I will focus more on quantum key distribution, which is quantum cryptography, because that's what we do in BeQCI. And we'll just go over BeQC very quickly, because you will hear a lot about BeQC in the next talks. So quantum key distribution quantum cryptography is basically quantum key distribution. The main task, task that is performed is quantum key distribution, which is basically using the first scheme that I show you, so going back before the 70s, so to private encryption schemes, but to solve the problem of distributing the key. So instead of meeting up, Alice and Bob can obtain a secure key in another way through a communication channel. And this is called quantum key distribution. This is done exploiting the properties of quantum mechanics, like the no cloning principle that says that you cannot clone quantum states, or the Heisenberg's uncertainty simple, to obtain unconditional security. And again, this is a way to distribute. This is more, as I was saying, requires dedicated hardware, but dedicated hardware that it's not as far away as quantum computer, let's say, because we already have manufacturers that produce commercial devices. Big names like Toshiba or IDQ that have been doing it for many years, but also new startups and also satellite ones, and many more. This is, of course, not exhaustive. It's just to say that there already are manufacturers that develop and sell commercial QKD devices. More than that, there's also deployment. So people are already deploying, like in China, for example, they built 4,000 kilometer backbone, QKD backbone, or in the UK, together with Toshiba, they are developing a QKD network, and also in Europe with the EuroQCI initiative, of which BeQCI is part of. I will skip, let's say, post-quantum cryptography, quickly saying that it's the other solution. It's basically using a different algorithm, so still public key cryptography, but a different algorithm, which is also hard to solve for quantum computers. And you will hear about it in the next presentations. I will just then give a quick word about BeQCI. So we are talking about deployment in a real scenario, and that's what we do in BeQCI. BeQCI is the first Belgian QKD testbed. It's a co-funded project. It's a project co-funded by the European Commission and Beltspo, and it's part of this bigger EuroQCI initiative, which aims at deploying a QKD network throughout Europe. And this is just the first step, which is done in every member state, and BeQCI is the Belgian one. And it's part of it is deployment of QKD technology for real use cases. But we also have research, a research part which aims at pushing technology further and exploit Belgium's strengths in the research environment, like in photonics or silicon photonics engineering or BeQCI, for example. And we also have a lot of dissemination activities like today's webinar and preparations for the next phases of EuroQCI. And about the deployment, I just wanted to show you what we are doing and what we've done and what we will do. So we already have deployed some QKD links, one between two campuses of Ghent University for research purposes, one used by Belnet to transfer data between two data centers. And we also have a cross-border connection, cross-border link between Redu and Luxembourg, and another link between Redu and Transine used for IoT applications. And in the future, we are planning to deploy more complex network topologies and use cases. Like in Brussels, we have use cases with IBZ and CityMesh, and we also will deploy a use case in the Asselt area with the hospitals. And we will also have a post-quantum cryptography data transfer use case between Brussels and Redu. And it's important to note that we also have this cross-border connection with Luxembourg, which is the first part of this development in the future with more cross-border links. In particular, I wanted to just highlight that we are looking for use cases. So if any of you has a use case, and is interested in knowing what we do, please contact me for this project, but also for the next phases of the project, which are already being discussed, which will be basically, there will be a shared project in the Benelux area to create a backbone between the Benelux countries, so going from Amsterdam to Luxembourg. This is in discussion. The call is already open. We are preparing it, and these are the next phases. So if you have any use cases, please contact me. And yeah, with this, I just conclude. Thank you all for the attention, and I'm open for questions in the future and leave the stage to the other presenters.